We are looking at page 119 in our student journal, section 4.9. What we're looking at today is something called finite differences. So finite differences, the definition of them are the differences of consecutive y values when the x values in a data set are equally spaced. So here's the key on this. We're looking at the differences in the y values, but the x values must be equally spaced for any of these rules to hold true. So our goal then is to figure out, based on these finite differences, whether we have a linear function, quadratic, cubic, or quartic. And we can tell that by looking at these finite differences. The reason that helps us is because of these properties. If a polynomial function has degree n, then the nth differences of function values for equally spaced x values are non-zero and constant. So what this is saying is, if I look at the differences in the y's, if it's a linear function, the first time I look at those differences, they're all going to be the same. If it's a quadratic function, I'm going to have to find the differences twice, and then they're all going to be the same. So it says, conversely, if the nth differences of equally spaced data are non-zero and constant, then the data can be represented by a polynomial function of degree n. So we're going to look at this with a quadratic because I want you to see what these finite differences are that we're talking about. Okay, so we say for f of x equals 2x squared plus 3, we're going to make a table of values. We're going to have x and f of x. For x, we're going to go with -2, -1, 0, 1, 2, 3. Those x values are equally spaced. I'm going to plug in. So if I plug in -2, I'm going to get 4 times 2 is 8 plus 3 is 11. Plugging in -1, I get 2 plus 3 is 5. Plugging in 0, we get 3. Plugging in 1, we get 5. Plugging in 2, I get 11 again. 3 squared is 9 times 2 is 18 plus 3 is 21. When I'm talking about the first set of finite differences, I'm looking at the y values. We're saying how do I get from 11 to 5? I go down 6. How do I get from 5 to 3? I go down 2. From 3 to 5, I go up 2. From 5 to 11, up 6. From 11 to 21 is up 10. I look at this first level of finite differences, and they are not constant. They're all different. So therefore, this cannot be a linear function. We already know it's quadratic, but we're just going to look at these finite differences and see what happens. To go from -6 to -2, I'm going up 4. From -2 to 2, I'm going up 4. 2 to 6, I'm going up 4. 6 to 10, I'm going up 4. This was the second set of finite differences. See how now we've got them all constant, they're all the same? So we notice that the second finite differences yield a constant. So it took us to get to the second level to get that constant value. So that's what's always going to happen in the quadratic. The second set of finite differences will all be constant. We're going to go over here now to page 120. Let's look down here at the bottom first. We're going to do 5 and 6. These are already in your student journal. So it says for exercises 5 and 6, use finite differences to determine the degree of the polynomial function that fits the data. Then use technology to find the polynomial function. And then we're going to do number 10 on the next page. All right, so we're going to look at our finite differences here. So from -14 to -6.5, to do that, we're going to have to go up 7.5. To do this, we're going to have to go up 6.5. Here we go up 5.5, 4.5, and 3.5. Is it linear? No, it's not all the same. Now we're going to look at them again. That's down 1, down 1, down 1, down 1. So what does that tell us then about this data? It has to be quadratic. So now we're supposed to find the quadratic function for this. So we're going to go to y equals, I'm going to clear everything out. I go to stat, edit. If anything's in there, clear it out. Go to the very top and hit clear. We're going to put in all the x's. -2, -1, 0, 1, 2, 3. Arrow over, go to L2. You're going to put in all the y's. -14, -6.5, 0, 5.5, 10, and 13.5. You want to double check and make sure you have the same number in L sub 1 as you do in L sub 2. All right, so now we're going to have the calculator come up with the curve of best fit. So we're going to go to stat, calculate. We just said it's quadratic, so we're going to go down to number 5. If I want to have it store for me, right here where it says store regression, I can tell it to store it into y sub 1. We're going to go to vars, y vars. It is a function, y sub 1. So now I'm telling it to store into y sub 1, whatever equation it comes up with. We go down to calculate, we hit enter. And here's what it gives us. R squared, the closer it is to 1, the more quadratic it is. This is a perfect quadratic equation. Now, this is the best place to find your equation. Once again, this is the best place to find the equation. So my equation is y equals -0.5 x squared plus 6x. Now, this right here is 8.1 times 10 to the -13. 8.1 times 10 to the -13. That is 0.0. That's what that number is. You don't need to write that down. But what do you think that really is? 0. This is 0, guys. When the calculator gives you a number like this, it is 0. Okay? Because this is 8.1 times 10 to the -13. That's a 0. So this would be our equation. So this is the problem with having the calculator put this in for us. Go to y equals. Look what it puts in. It's a little bit of a ridiculous equation that it puts in. It tries to be so exact that it's making the answer worse. This is the exact solution. So I don't like storing it like we used to. I'm just going to clear it out. I'm going to put it in myself. Now, I want to be able to see my points and I want to be able to see my graph. So I'm going to go to second y equals and I'm going to turn on my stat plots. I'm turning them on. So now they're on. Now I'm going to, if I just hit graph, I'm not going to see everything maybe. It's not horrible. That's an okay graph. But if I do a zoom stat, it's always going to make it so that I can see every point that I put in there. Sometimes I can't see it coming back down, so I'd want to extend my window to maybe be able to see it, the quadratic come back down. But that's always a good starting point, is to do a zoom stat. Okay? All right, so let's look at number 10 now, guys. Or 6, rather. On number 6, the x's are evenly spaced. This is going to be down 26. This is down 4, 0, down 14. Definitely not linear. I go to my second differences. This is going to be up 12. This is up 4. This is going to be down 14. This is 22, sorry. Okay, so it's not quadratic either. So this now, we're going to look at our next differences. This is going to be down 16, or 18 rather, and this is going to be down 18. So what does that mean this function is? Here's our first differences. Yeah, it's going to have to be cubic. So this must be cubic. So let's go ahead and find this cubic equation. Do it on your own. I'll be doing it up here. So this is a good example. I already have my stat plots on, but if I just hit graph right now, I'm not sure I'm going to see all those points. And look what I'm also seeing, that old quadratic function I put in. So that's why you want to be sure to go to y equals, clear out what you had, and you want to do a new zoom stat to be able to see these points. Okay, so I can tell it does look pretty cubic. So I'm going to go to stat, calculate. I'm going to go down to the cubic regression. I'm not going to have it store because it does not do a good job at that. And here we go. It would actually been probably fine on this one, but so my cubic function is y equals negative 3x cubed plus 2x squared plus 1x. The d value is 0. If I want to check it, I just do a graph, and if we've done it correctly, it should go through those points very well, and it does. Any questions so far? All right, let's skip over now to number 10. The table shows the value in thousands of dollars of a signed autograph of an MVP football player, where X represents the number of years since 2000. Find a polynomial model for the data for the first 5 years. Use the model to estimate the year that the autograph will be valued at $5 million. So I check the X's. They're going up by 1. I'm going to look at my differences. Let's say we don't want to look at our differences. What else could I do if I don't feel like checking all these differences? I could just put it in and I can just guess and check. Let's do this one that way. We're going to go to Stat, Edit. What do you guys think this is? Is it linear? Could it be linear? Could it be quadratic? Probably not. Do you think it's cubic? Maybe. Let's see. So we're going to do a stat, calculate. We're going to see if it's cubic. Going to go down here, calculate. That r squared is pretty close to being cubic. It's not bad. But let's see if we can do better. Let's go to stat, calculate. What comes beyond cubic? Let's try quartic. All right, that's even better still. So we're going to want to go with quartic. If you checked these differences, the first don't match, second don't match, third do not match either. Fourth, we end up only having one value, so we can't even know for sure. So we would just have to kind of do a guess and check type of method. So here's our model, y equals 2x to the fourth. This is 0, this is 0. This is really just negative 2. So x cubed is 0, x squared is 0, x is going to be negative 2, and then my constant's just going to be 6. This is the equation. I'm going to put it in. I'm going to do a zoom stat. So here's my equation and there are my points. Now, if it says to use the model to estimate the year that the autograph will be valued at $5 million, but these are in thousands. What am I really looking for? Not 5 million, but what? How many thousands are in 5 million? 5,000. Close. 5,000. Because if I multiply this by 1,000, I get 3 more zeros, and that's 5 million. So we go to y equals. We just have to put in 5,000. We graph. We don't see it, and that's because we have not adjusted our window. So on our window, I probably want this to go out to like 10 years. And I definitely need my y max to go up to at least 5,000. I'm going to make it 6,000 just to be sure. So here's our model. Here's our polynomial model. Here's y equals 5,000. And now we just need to find the point of intersection. Let's get up there close to it. Enter, enter, enter. So it's 7.07. But what year would that correspond to? This is the number of years since 2000. So what year would I actually put? 2007. In that year, that's when it's going to be valued at $5 million. All right, we're going to go back now to page 120. I want to do a couple of problems over cubics where we do not use our calculator. This would be on the non-calculator part if we had that on our test. So it says, for numbers 1 and 4, write a cubic function whose graph passes through the given points. So we're given 3 points, but we're not allowed to use our calculator. Here's what we can do. We know it's going to have to be y equals a. We don't know what the a value is. If this is going to be a 0, what was it as a factor? If the 0 is -1, what was the factor? X plus 1. All right, guys, this is another 0 right here at 1, 0. What was the factor? And then it's going to have to get, if it's a bounce, what happens? It's got to be squared, right? So we know all of this would be right, but we don't know the a value. So I have to put in a point other than the x-intercepts. So they gave us a point right here. So if I use the x-intercepts, I'm just going to get 0 equals 0. But if I put in 3 for y, 2 for x, and now I can solve for a. So I get 3 equals, 2 plus 1 is 3, that's 1. 3 times 1 is just 3a. So a just ends up being 1. So now I know my equation is y equals just x plus 1 times x minus 2 squared. Now if I'm taking a test and I want to make sure that's right, I can just go in here and I can put in x plus 1 times x, I didn't mean x minus 2, x minus 1, times x minus 1 quantity squared. And now I can just look at my table and I should be able to see these points, -1, 0, 1, 0, and 2, 3. So now I know that equation is right. If I'd kept the -2, which was wrong, I wouldn't have seen those points. All right, so now we're going to do this one. This is really number 4. These numbers got messed up. Okay, so let's talk about our zeros, because that's how we get our factors. So we know it's going to be y equals a. What's the first one going to be, guys? The first factor, x plus 2, good. Next one, last one, good. Now what do? Put in what point? Yep, so I'm going to put in 3 for y, a I don't know, put in 0 for x, so I'm going to have 2 times -1, that's -2, times -3, that's going to give me +6. So what's our a value going to be then? 1/2. So now our equation is y equals, put back in the a value, but just leave everything else as part of the equation. So guys, this is called factored form of the cubic function. What if I said it had to be in standard form? What would you have to do? Multiply it all out, yeah. So I would always ask for this type in factored form. All right, so we talked about the finite differences. If we get them all the same on the first level, it's linear. Second, quadratic. Third, it's cubic. Fourth, it's going to be quartic. And then we also talked about how to find the a values in here. And that's it. Your homework is on Canvas.